All right, second session of day 2. We're going to start off with Susan Athey, and Susan is a titan. She's the Economics of Technology professor at the Stanford Graduate School of Business and a research associate at the National Bureau of Economic Research. She's made fundamental and path-breaking contributions in so many fields of economics, I actually had to write them down to try and make sure I had a semi-complete list. Market design, auction theory, mechanism design, econometrics, the economics of the internet. It's awesome. She holds a number of awards and honors. She's a member of both the National Academy of Sciences and the American Academy of Arts and Sciences. And in particular, she received the John Bates Clark Medal, the highest honor given in economics to economists under 40. On a more personal note, it's an extreme honor for me to introduce Susan because she was not only my advisor in graduate school, but one of my advisors in college. So she's the first person who introduced me to the field that I now work in as my main research focus, market design. And for that, I'm forever grateful. So we're honored to have her here. She's going to speak on machine learning and causal inference for policy evaluation.
Scott, thanks so much for the lovely introduction. Let me try that again. Thanks so much for the lovely introduction. Now the mic's on. So I'm really happy to be here, and I'm going to be talking about some research that I've been doing together with a number of co-authors about how to combine techniques from machine learning that are ideal for big data with some of the goals that social scientists, and especially economists, are most interested in achieving. Let's see. The clicker doesn't want to click, so maybe, why don't you see if I've not got it on?
Huh. I don't know. Why don't you, is it clicking by?
I can use a keyboard, yeah. So I got interested in this line of work when I started working as a consultant with the Bing search engine in 2007. And when I got there, I encountered a world full of people doing statistics in a language different than what I was familiar with in economics and econometrics. And it took a couple of years, really, of collaborating as sort of a lone social scientist and an economist with a large group of machine learning folks for me to kind of even organize for myself what I thought were some of the key strengths and weaknesses of the different fields. And so I'm going to make some generalizations here as I overview, but you can sort of take them as stereotypes as you will. But what I found from what was present in the supervised machine learning literature that was really absent from microeconometrics and a lot of the social science work were the non-parametric prediction methods that worked well with big data. And in particular, some of the techniques like cross-validation for model selection or regularization. And that is something that a few subfields of economists had started to take a look at, especially in time series econometrics, which is mostly about prediction. But in cross-sectional econometrics or applied econometrics, where we're trying to answer questions about the world using observational data, that has just been completely absent. On the other hand, a weakness which everybody is becoming a little bit cliche to criticize machine learning for, but it doesn't have as much of a focus on causality. Of course, there's notable exceptions like Judea-Pearl, and there's, of course, a large subliterature there. But the kind of bread and butter, middle of machine learning theories and methods really were not designed to deal with causal inference as their first priority. They're more about prediction. On the other hand, within econometrics, social sciences, and statistics, I found that some of my tools were surprisingly, to me, unfamiliar to the machine learning community. For example, structural models that predict what happens when the world changes. And so in my fields, like a lot of my early empirical work in auctions was done in this kind of paradigm where you try to estimate the preferences of the players in a game and then make predictions about what would happen when the world changes. So I had some very interesting debates with some of the machine learning scientists that I was interacting with when I was trying to predict what advertisers would do in advertising auctions. And at first they said, oh, you're just telling me it's a very hard prediction problem, so we just need a more complicated model to fit the past data to predict the future. And then after some back and forth, we finally kind of came to a language where I could explain why that was not at all going to work. And the language was basically that, well, I'm going to change the world in such a fundamental way that the joint distribution of the features and the outcomes is going to change. Okay? Because if I change the game, if I switch from a generalized second price auction to a Vickrey auction, or if I change the reserve pricing policy, then the relationships among the variables in the past will be unstable. And so once we finally got to that point, my machine learning friends then said, oh, well, you're not a scientist, you're a quack, because nobody could possibly do that. If the world changes, you have to retrain your model. Duh. Okay, and so then I explained, well, that might work in certain contexts, but if you're the Department of Justice trying to decide whether Staples and Office Depot should merge, if you're Bing or Google trying to decide whether they should move away from the generalized second price auction, which is kind of broken after many years, and move to the Vickrey auction, like Facebook now runs, you should, that's like, all of Google's revenue is coming from these ad auctions, and you would like to have a prediction about what would happen when the world changes. And you can't just, well, let's change the whole auction, rewrite all the code, disrupt my $40 billion business, and then retrain my models. That doesn't work. So basically, like what the social scientists have been in the business of for many years is figuring out how to do this impossible task and do it as well as we can. Given that it's such a hard task to predict what happens when the world changes fundamentally, there's actually lots of debates within economics and social science about the best way to do this. So some people want to do it with a very minimal number of assumptions and then get very wide predictions. Other people want to make more assumptions and get more precise predictions. And like in some of my work, you might combine techniques. There's certain questions that I can answer without a lot of assumptions. But if I want to look at, say, the welfare of the parties, I need to make more assumptions. And so I'm going to make those assumptions for answering those questions. And when I say the welfare, the well-being, this is something that platforms really need to measure. So Google or Bing or Facebook or Amazon, they all need to understand the welfare of the participants on their platforms, their sellers, their advertisers, and so on. Because if they make them unhappy, they'll go away. And that's bad for long term. But again, you can't run a short, at least the standard A/B testing experimentation platform systems don't do a good job testing those kinds of things because they're long term. It takes time for a market to adjust. It takes time for a seller to say, oh, forget it, I'm not bothering with eBay anymore. And it's very expensive to do that kind of experimentation. So these structural models can be quite important, but they're hard. Now, within economics and social sciences, you have these fierce debates about how many assumptions to make and so on. But actually, from the world of machine learning, they all look the same. From far away, they're all about making counterfactual predictions when the world changes, and it just kind of details how many assumptions you make. So I thought that was kind of an interesting perspective. We're more united than we thought we were. We were worried about little details of differences of what we do, but actually, it's all very unified in terms of its goals. And of course, in statistics here at Harvard, we have the formal theory of causality, the potential outcomes method of Don Rubin. My husband and co-author, Hito Imbens, has just released a great book on the kind of the Bible of causal inference. So all of you who haven't read it should pick it up. So we're very good at thinking about how to do causal effects in experimental and observational studies. And one of the interesting observations there is that some of our very standard bread and butter toolkit techniques that we teach all undergraduates the words are not even familiar in the machine learning audience. As an example, I gave a keynote at KDD, the big machine learning conference, a couple weeks ago in Sydney, and I asked people to raise their hand if they'd heard of instrumental variables. Only like maybe 5% or less of the audience had heard of it. And it's a technique that is just completely standard in social sciences for dealing with observational settings. So I won't actually be able to go into that today, but it's just an example that where there can be cross-fertilization. But where we're really bad is thinking about model selection. We tend to craft our models by hand very carefully, and that kind of works. There's only so far wrong you can go if you have, I have 300 timber auctions and 15 covariates, and maybe one of them is really important, and so I do a flexible functional form for that. But basically, we're crafting the model by hand, and we're kind of exploring the data to find the model, but it's not. There's only so many things we can do. What I found is really my first motivation to write the paper I'm going to go into today, as well as really to explore this whole area, occurred when I was trying to study advertiser behavior at Microsoft, where I was studying it with Dennis Nekopolov here. And we were trying to predict advertiser behavior. And I was doing some simple descriptive analysis, and at first I sort of said, well, what if I look at all advertisers as a whole and say, see how they respond to a change? And I did a regression, like one single regression, everybody pulled together, and like you get a big, fat, noisy 0, you know, like it's wildly imprecise. So then you say, okay, well, maybe I'll segregate. I can't put the same regression with eBay and a small advertiser, so I'll make 10 buckets of advertisers by size, and then I'll run my regression. Well, that still was very messy. And then I kept working, and suddenly I was running like 10,000 regressions in parallel, and then I realized that, you know, there was a better way to do this. And so what was really the motivation there for the work I'm going to present today is that I still wanted to run my economic analysis with causal inference. That is, I wanted to know how a change in say, pricing or a change in some other rules of the auction was, how was that going to change advertiser behavior? So I had a little kind of an economic model, simple model, that I wanted to estimate. And where I wanted to use machine learning was to really absorb all the heterogeneity out there. The advertisers were different in so many different ways, and so I still wanted to keep my econometric model, but I wanted to have it be highly heterogeneous. And so what that motivated me to do was develop some new techniques. So let me just, before I go into the details of the paper, I'm going to give a little bit of more big picture overview, the model for causal inference, and I'll talk about the research agenda the paper fits into. So for causal questions, we want to know what happens if a policy maker changes a policy. Administer a drug, change a minimum wage law, raise a price. And the fundamental problem of causal inference is that we don't see the same units at the same time with alternative counterfactual policies. So I could give this side of the room aspirin, I can give this side of the room no aspirin, I could take all your temperatures, but the people I gave aspirin, I don't know what your temperature would have been without the aspirin, and vice versa. And so one of the things that's been a big focus of the Rubin, Imbens et al. Literature is that we're going to imagine that those effects are heterogeneous. So for each one of you, there's an individualized potential outcome for having aspirin and not having an aspirin at this very moment in time. You all have your own treatment effects. And I don't want to assume that they're all the same. And so then I want to think about how to estimate those. So we use the Rubin causal model. It's basically just functional notation. So we're going to say yi of w is the outcome unit I would have had if assigned to a treatment w. So if you didn't get the aspirin, your outcome would have been yi of 0. If you did get the aspirin, it's yi of 1. In a more complicated model, like a demand system, it could be that yi is like how many units you buy, and w might be the price that I impose upon you as the seller. For the binary treatment, which I'll focus on today, we'll use the notation tau I is the individual treatment effect for each person. And the key thing that's going to make all of this work hard is that tau I is unobservable for everybody. So I do not know Scott's treatment effect. Okay? And I never will know it for anybody. And so what I want to try to do is get all the beautiful things we have from machine learning when we actually know the ground truth for a test sample, and we can use cross-validation for regularization, and I want to apply that in a world where the thing I want to estimate is not observed. So that's the key problem, and as far as I know, we're the first ones to really try to confront that head on. So in the notation, we're also going to have units of study having fixed attributes x. These would not change with alternative policies. So in other words, we don't contemplate moving coastal states inland when we change the minimum wage policy. When I change pricing policies in an online auction setting, I'm not imagining that the distribution of characteristics of the people, at least the potential sellers or the potential users in my marketplace are changing. I want to understand what happens for people with these fixed attributes. And actually, we're going to find that that's going to make a difference for everything that we do, distinguishing between a W, which is a cause or something that we're going to manipulate and we want to get a causal effect for, and the X's, which are things that are held fixed. And so one of the talks yesterday, we saw examples of trying to think about like testing for the assumptions that were required to do causal inference if you had, potentially tens of thousands of covariates that would all potentially could be exogenous. And here, one thing I want to emphasize is that in economics and in social sciences, observational studies, we don't usually think that we have more than like one thing that's possibly exogenous. Usually, like all the characteristics of people are correlated with their potential outcomes. So if you're a healthy person, that's correlated with your temperature with an aspirin as well as your temperature without an aspirin. If you've studied hard, that's correlated with your potential wages. So we have lots of covariates that are absolutely patently not exogenous, and therefore you cannot do causal inference on those things, and we wouldn't even try. And those are the kind of things we're talking about here with the attributes. Those are things we want to soak up. We can think about dividing populations by your income or how much schooling you've had or whatever, but I'm not going to get a causal effect of those things because I have no exogenous variation. There's no random assignment of that variable. Instead, we might, if we had a field experiment or an online experiment, A/B testing type of environment, I might have one thing that was exogenous. Or sometimes when we use instrumental variables, we have something that helps us, like a draft lottery number helps us understand the effect of going to war. But we might only have one or two of those things. And so that's one reason I just want to highlight that my methods are it's going to be really useful to draw this line, because I don't need any assumptions about most of my covariates. I don't need them to be exogenous. I don't need them to be unrelated to potential outcomes. I only need the thing that I'm actually studying, which might often be like one dimension and maybe a 0-1 variable. Okay, so I'll just very quickly sort of talk about the research agenda that we're working on. And actually, I realized here I'm doing some new work with a co-author in the statistics department, a brilliant graduate student named Stefan Wager, who's graduating in statistics this year. And I didn't put up yet on this slide our recent work in progress, because we haven't actually quite released it yet. But, so sorry, Stefan, for the omission. So the problems, many problems in social sciences have this combination of prediction and causal inference. And so a lot of the existing machine learning approaches don't directly apply to estimating causal parameters, but what we're going to show is that with a little bit of modification, we can take all the machinery that we already had and apply it to causal inference. But some machine learning methods are better than others if your ultimate goal is to try to test a hypothesis. So the other thing that's different about what the most important goal from a social scientist perspective is that we want to get statistical significance of something, or we want to know whether we can actually trust the results. And so for estimating the effect of the minimum wage policy, it's not enough to say, the minimum wage would be good for counties like this and bad for counties like that. I need to know if there's confidence in those results. And so a lot of machine learning methods, nobody's ever written down the formal asymptotic theory of the predictions that come out of there. And that's what I'm working on with Stefan Wager for the random forest, among other things. So then the proposals we have are to formally model this distinction between causal and predictive parts of the model and treat them differently for estimation and inference. So I have a paper that's under review right now that's basically exploiting that to show that the way that we do standard errors in inference in the basic linear regression models is actually wrong for the problem of causal inference. And so that's because the nature of the missing data problem, or the nature of what's unobserved, is different for a causal parameter than an attribute. So if I observed my whole population of individuals, if I see the whole population, then I'm not doing a random sample from that population. So if I had data from this room, I could tell you exactly, and I took all your temperatures, I would know exactly what the difference in the measured temperature is between men and women. There'd be no sampling from, if my study was this room, I would know exactly that difference. And of course, in many online settings, you might observe your whole customer base or your whole seller base. On the other hand, I'm not going to know with certainty the causal effect of an aspirin for this population, because I'm never going to observe it for any individual. So there's still an inference problem left. And so what we show is that from that, it's very important to write down what is the population you're drawing from and what is the source of uncertainty in your model, and it's different for attributes of individuals than it is for causal inference. We're also working on a series of papers where we try to, the bigger theme is that we have machine learning approaches for the prediction component of the models, which is usually about soaking up the X's, and the economic model for the causal inference. And we apply that to look at robustness, we apply that to look at policy estimation, and so on. A couple of other lines, we're looking at doing analysis of A/B testing on networks, and Hito Imbens is going to present that here tomorrow. And large-scale structural models with latent variables, some work that I've done with Denis Nekopolov, as well as with David Bly and Jake Hoffman, two computer scientists, where we're trying to build these large-scale structural models that predict counterfactuals. So now let me jump in and give more detail on one specific paper, which I think illustrates the approach that we're following in maybe the simplest case. So the first motivation here, and this really came up a lot yesterday as well when people were talking about how to draw inference from data. There's a lot of concerns about ex post data mining, and this is the bad version of data mining, on studies, either large-scale experiments or observational studies. So in medicine, scholars are required to specify pre-analysis plans, and yesterday, we saw that was kind of presented as the ideal. Like the ideal way we do empirical analysis is that we have a pre-analysis plan. I agree that that's the ideal if you want to make sure you don't overfit in fish and find spurious results. But it is actually not it's not a realizable scientific ideal in the kinds of settings that I look at, and I think for large-scale analysis, because there's all these covariates out there, and how could we possibly have a theory about exactly how they all interact with each other? In some sense, I think the ideal world is actually that it's data-driven, that it's not biased by our theories if it's something that's potentially discoverable from the data. But rather, we have to have a technique that's really, really careful about doing that properly. Now, it's going to be really hard because once you open that door, there's always a meta level where you kind of change the modeling framework or the robustness framework. So I cannot stop researchers from manipulating entirely. But I think that you can possibly have methods that will solve these problems. So that's really our goal, to allow a data-driven search for heterogeneity and causal effects with valid standard errors. Where we're getting unbiased results and we can actually test hypotheses and the statistical significance means something. Second, we just want to think about actually estimating the function. What is tau of x? What is the treatment effect? The average treatment effect is a function of x. And so that can be useful for a whole variety of reasons. If you're trying to derive an optimal policy, then if tau hat of x is positive, you want to give the policy, and if tau hat of x is negative, you don't want to give the policy. So it turns out the methods are almost the same, but slightly different if you want to estimate an optimal policy and minimize the loss, and I'll talk about that later, and estimate the function itself. I'm going to focus first on estimating the function itself. And if you want to think about this tau hat of x function, the price of aspirin may change, but I want to know this fundamental economic parameter, which is what are the benefits of aspirin, and I want to estimate that, and then I can apply it to optimal policy evaluation in lots of different circumstances. So it's a more, estimating sort of the benefit function, say, might be a more primitive economic parameter that's more generalizable than the optimal policy in any moment. And here I'm going to maybe do one other bit of perspective. So we're going to propose a method based on trees. And often machine learning people ask me, well, why on earth would you use a tree? Because that's not the best prediction algorithm. And so I think there's a real trade-off into what method you use as to what your objective is. So if I'm going to put a computer in every doctor's office, and they're going to punch in the patient characteristics or scan them and have it go in the computer, and the computer is going to come out and say, give the drug or don't give the drug. Right? Then I basically want the most fine-grained tau hat of x I can have. I want to get the best prediction for every individual, one at a time. And for that, a version of this paper that I won't present today with random forests or some other non-parametric method, kernels if they worked, or something else, would be the right way to do it. I just want a black box algorithm that's going to give the best prediction for every individual. Or if I'm doing direct mailings or phone calls or some other thing where I'm going to have a computer kind of do all the allocations, and all I care about is how well the computer does. On the other hand, if I'm trying to, going back to medicine, if I'm going to tell doctors, like, here's a decision tree that you're going to put on a poster on your wall, So, if the patient is of this age and they have these symptoms and they have this, then you give them the drug, then that needs to be simple. And so I might as well directly go after the best kind of simpler and interpretable rule. And I also might want to, if I just do my analysis, I might want to explain it to you, and I can't really explain my black box to you. The standard in machine learning is you say, oh, cool, I've got a really low mean squared error. I'm so much better than the last one, but then you don't really have much to show in terms of your results. And what I'm going to show you now is going to give you interpretable results. But I want to say I don't have a religious attachment to one or the other. I think that each of them has their place in different settings. It turns out the inference is easier for the trees, and so we still had to do a lot of work to make, say, random forests have valid inference. Hopefully we've got that all worked out, and that'll be with Stefan Wager, we'll be releasing that soon. Okay, so we're going to distinguish between causal effects and attributes. We're going to estimate treatment effect heterogeneity. We're going to introduce and analyze new cross-validation approaches for causal inference, and that's kind of the part that's technically new. And then we're going to do inference on treatment effects in subpopulations, which is just something that the machine learning literature, that's just a question they haven't asked mostly, at least in this part of it. So we're going to do regression trees. So regression trees are really, I think, attractive for interpretability, which is one reason they're used in business analytics and practice, a lot of real-world settings, even though they're not the best predictors. So what a tree does is it partitions the covariate space into leaves. And then it's a really simple model. You predict your outcome conditional on the realization of X based on the average outcomes in the leaf that you're in. And so it's really nice because there's no kind of spillovers across the different areas of the space. Like if I see a leaf and I say this is people over 65 who live in the South, then I know exactly why my prediction is what it is. It's just the average of people like you. So it's highly interpretable. And it gives a lot of intuition. And then you select the complexity of the tree using cross-validation. So I have a little chart here that kind of, or outline that goes through some of the key components of this because I'm going to change the things in red. So the standard tree, there's an estimator, and yi hat, the prediction, is the sample mean of yi within a leaf. The in-sample goodness of fit function, how you decide to split one leaf into two leaves, is based on the mean squared error criteria as well. And then the out-of-sample goodness of fit, so when I cross-validate and see is my tree too complex or not, I'm going to compare models using mean squared error out of sample. And so the key thing that makes this work, as well as many, many other machine learning techniques, is that you have the truth. So for my test sample, I know yi. So I can say, does yi hat fit yi? And if it doesn't, then I did a bad job predicting. So I know the ground truth. So now let's think about using trees to estimate causal effects. I'm going to have yi is going to be my potential outcome function. Just for the talk, I'm going to focus on random assignment of the wi, but it's easy to extend to observational studies under the assumption of unconfoundedness. And we have another version of the paper for instrumental variables. We want to predict individual i's treatment effect, tau I, and it's not observed for any individual. So we can think there's a big regression function, mu of wx, which is just the average outcome conditional on w and x. And tau of x is the difference between that function evaluated at w equal 1 and w equals 0. So you might think, well, what would be the conventional ways to do this? And most of the people from stats and machine learning, it's a small group that's been attacking this problem, have been attacking it roughly in one of two ways. The first way is that you analyze the two groups separately. So I take the treated guys and I take the controlled guys, and I fit a model for both of them, and then I take the difference. Okay? And so there's a bunch of people who've proposed that. The second approach would be to estimate one big model, both as a function of w and x, and then just construct the prediction by substituting in w equals 1 and w equals 0 and taking the difference using your predicted model. The weird thing about that is that it's going to estimate a zero treatment effect anywhere the tree doesn't split on w, or it's going to find, certain interactions are just going to be sort of ruled out. So the observations for this are that the estimation and cross-validation are not optimized for the goal. The goal is to estimate a treatment effect, not to estimate a level. And so if your model is saying, I want to split, or I want to select variables, or I want to compare models according to how well I predict my y, then you're asking your machine to optimize something, and it's going to go to town optimizing that. But if it's not the right thing, you're going to use all your degrees of freedom optimizing the wrong goal. And so this is a really big issue empirically, because in practice, there are often many, many observables that affect the level of your outcomes that don't affect your treatment effect. So, if I know your weight and your ethnicity and your gender, I can predict your temperature very well. But that might have nothing to do with the causal effect of aspirin. Okay, and so you're going to use all of your degrees of freedom sort of predicting how your levels change, and you won't have any left to soak up variation and heterogeneity. So one way to do that is, like, if you're doing lasso or something, is you could use different penalties for the interaction effects and the regular variables, and so that's something that has been discussed. But it's ultimately still your cross-validation is not really tuned to your goal. So we want to think about how to do that, and we're going to start with a way that works but works badly, and then we're going to propose ways that work better. But let's just start with the bad way of working. So it turns out that, so remember, the goal is I want to find the ground truth for everybody. So let's suppose Scott got an aspirin. Turns out an unbiased estimate of your treatment effect of the aspirin is 2 times your temperature. Okay, so your temperature was 98, so 2 times 98, that's an unbiased estimate of Scott's treatment effect. If Dennis didn't get an aspirin, then minus 2 times his temperature is an unbiased estimate of his treatment effect. So if I think about averaging them all up, then I'm going to get the treatment effect if you just do a little bit of algebra. So if just to see that, I've done the algebra here on the second line of notation there. If I think about what's the expectation of this yi star, well, half the people are going to get 2 times their outcome, half the people are going to get minus 2 times their outcome. I average them up, and I get the average treatment effect. So that works, and so we're going to first say, well, let's try that and see what happens, but then see how we can improve on it, because it's a super high variance approach. And of course, there's nothing special about the 2. It could be a 30% treatment. It could be something where the treatment depends on your x's. You just have to adjust it for the propensity score. So the method that we're talking about next is it's a conventional tree, or any conventional machine learning method. It can be applied to anyone with a transformed outcome. So in the case of a tree, my estimator, a tau hat of x, would be the average of yi star within a leaf. So if I have a leaf of people of male economists in the room, then I'm going to take the average of their yi stars, and that's going to be my estimate of the treatment effect for that leaf of male economists. I can use yi star also for my in-sample and out-of-sample goodness of fit measures. It's an unbiased estimate, but it's a very high variance estimate. So there's a few problems with this. First of all, like, if my male economist leaf didn't happen to actually have 50-50 treated and control, it would say it was 55-45 just by chance, then this estimator would take the mean as if it was 50-50 and not actually adjust the weights so that you got the average of the 45% control against the average of the 55% treated. So we would just get the weights wrong and make a stupid mistake, a high variance mistake, and so we want to propose to correct that. And to make the estimate within a leaf just the average treated minus the average control, rather than pretending that they were exactly 50-50. The second thing is that using the transformed outcome creates noise in both tree splitting and in out-of-sample cross-validation. And so we'd like to say, well, we'd like to find another estimate of your treatment effect that we can use better. So actually, in sample, it turns out there's a very easy trick so that we don't have to work so hard. So when you do classification trees, that you often split based on a Gini construct, where you say, if there's a lot of variance in the predictions of classifications within a split, that's a good thing. So if one leaf is mostly 1s and the other leaf is mostly 0s, then I should split. And so we can use the same idea here. If one leaf has a high predicted tau hat, and the other has a low predicted tau hat, that's a high variance predictor, and that's a good thing. We want our predictor across leaves to have a lot of variance. Because our predictor will be unbiased by construction in the training sample, we can just take the variance as an estimate of goodness of fit. So the variance of predictions, and it's like a Gini measure for the classification tree. Out of sample, we have a harder problem because the prediction is not unbiased out of sample. And so what we propose there is a nearest neighbor matching estimator, so that for Scott, I'll match him up with Dennis, and I'll take the difference between your temperatures as the ground truth. And that's going to be much lower variance, because if I'm going to account for your covariates, and I'm not going to do this crazy -1 thing. Okay, so that's our proposal. Sample average treatment effect within a leaf, variance across leaves as the way to measure goodness of fit in sample, and compared to a nearest neighbor matching estimator for the ground truth out of sample. So let me actually, in the interest of time, skip the simulations. The conventional wisdom is that trees are bad for inference, but that's because they're discontinuous. What I don't want to do inference about my tree. I want to do inference about the treatment effect within a leaf. And so there, actually, the tree is perfect because the construction of the tree is just going to be a way to partition my covariate space. And I'm doing that, and if I do that on a one sample and then estimate the effects on another sample, it's going to be just like any kind of function of exogenous covariates. I can do that. I can separate my data. I can analyze my data separately for men and women or anything else. As long as that's not contaminated by the data I'm using to estimate the effects, I'm going to get honest inference. And so we can call these honest trees, and I'm surprised there's been less emphasis on this in the machine learning literature because they work so well, and it's kind of obvious once you see it. But it's a very powerful approach. So again, I'm going to say estimate the structure of a tree, or do my model selection on half my data, and then I'm going to do the model estimation on the other half of my data. Now, maybe one reason people haven't done this is that sounds horribly inefficient because I'm throwing away half my data. But in fact, you kind of need to do something like that, or you won't be honest. you won't get unbiased estimates. And I'll show you some simulations where even in situations where you might have thought the bias wouldn't be a big deal, it is. So this is our idea. And then in the work that I'm doing with Stefan Wager, we're building up random forests with a collection of honest trees. And then we can use all of the data. So we're not really throwing out half the data, but it's just that every single one of our trees that builds the forest is constructed in the way that you use one set of data for the variable selection, the feature selection, and another set of data to estimate. And so this is, I think, a very powerful idea. People would cringe at it if you had 200 observations. Maybe they shouldn't, actually, in fact, but they might. But in a lot of cases with big data, you have lots of data, and you have lots of heterogeneity. And you'd much rather learn a small number of things that are true than use every ounce of your data and not be sure if any of those things are true. So that's kind of what I would say about that. Okay, so let me show you a couple of applications. So first I'm going to look at an experiment I ran on Bing where I looked at the effect of re-ranking search results. So search queries are quite heterogeneous. People are looking for different things and they have different click patterns. And so I'm going to show heterogeneity with respect to the characteristics of the query. And generally, there's actually been a lot of interest just in the last 6 months from tech firms and the methods I'm talking about now, because all the tech firms have a big A/B testing platform where they run lots of experiments. And so generally, the engineer works and they build an algorithm, and then, oh no, it doesn't work. They would like to know, well, it worked on some subset of the data, and they might do some post-analysis fishing of the data to see that. But what you could do in principle is take my techniques and build them into the experimentation platform so that it'll just pop out for the researchers where their algorithm worked and where it didn't. And then you might actually ship the algorithm and release it to practice only on the parts of the system where it works, and then go back and fix it on the other parts. So this makes the engineers very happy. So they're actually super excited to put this here because they'll get more, they'll look more productive, they'll release more things, and get more bonuses. Okay, so for the case of the treatment effect of position, this was done for the European Commission because we were trying to understand whether it mattered that Google manipulated results. So Google had admitted to the FTC and others that it was manipulating algorithmic search results in some cases, and we wanted to know whether that would matter. So the dark blue is the natural click-through rate of algorithmic search results in different positions. And then what we did was we flipped, in the treatment group, flipped position 1 and 3, or flipped position 1 and 5, or 1 and 10. So I'm going to focus on the 1-3 flip for my heterogeneity analysis. And what we see is that when you flip 1 to 3, the click-through rate is the sum of the dark blue and the light blue. So roughly, they lost half of their clicks. But they didn't go all the way down to the click-through rate of the third position, which are worse results. So this is also where you're seeing like endogeneity problems, that Bing ranked the results in a smart way. Therefore, you can't just look at the raw data to see the effective position. You do need to run a randomized experiment, and you get a different answer for the causal effect from the randomized experiment than from the observational data. So now I'm going to look at treatment effect heterogeneity. And so I build a tree, and it turns out the treatment effects here are highly heterogeneous. So in each box, I'm going to show the average treatment effect, its standard error, and the proportion of the population. So we see, for example, in this one of the far right boxes, that queries that were classified by classifiers to be high celebrity, high image queries had actually no treatment effect from the flip. And that's because, like, if you're looking for Britney Spears, you're actually not looking for information. Maybe you just want to see a picture or something else, and so the treatment had no effect. While for things that were classified to be better matches for Wikipedia informational queries, the effect was much larger than average. You lost 0.2 clicks instead of 0.135, which was the average. And so this is the bottom of the tree, so we don't have time to go through each one of these, but if you actually spend time studying it, a lot of them are quite interpretable. So a few more points I want to make. So here in this table, each line is a leaf. I've got treatment effect, standard error, and the proportion of the population. And so in the training sample, it turns out that the results on average are much more extreme than in the test sample. So the variance of the predictions is higher in the training sample than the test sample. It's 2.5 times higher. They're farther away from the average, which is minus 0.13. And so what you see is that this is overfitting. Even in this thing where I had 500,000 observations and I've only got 20-odd leaves, there's still an overfitting problem in the training sample, and you're going to get different results if you do my sample splitting thing. So let me show this again, and I'll close up with this example. It's an American Economic Review paper by Carlin and List, where they did a field experiment for charitable giving. They offered various kind of matches and example gifts and limits in the mailings. And they found that offering a match increased the gift amount, but larger sizes don't have an incremental effect, and this is interpreted sort of as behavioral economics, that people weren't responding to the prices. So what I did was I downloaded their data, which they made publicly available, thank you, and I tried to look at heterogeneity of the treatment effect. So this is what a tree looked like in the training data. And so it turns out that the treatment effect heterogeneity is not very robust here. So actually, as I sample different samples of the training data, I'm going to get different looking trees. And sometimes it prunes them all the way, and it says, no, you shouldn't split your tree, and sometimes it says you should. So here's a case where it says to split the tree, and according to the probability of being black, the percent that voted for Bush, the probability that people are a homeowner, and so on, you're going to get different treatment effects of this solicitation for donations. What's interesting, this is in the training data, and so I can first run a regression where I put in dummy variables for each of the leaves in the regression, and you see, first of all, that the bottom parts are the interactions between the treatment effect and the leaves, and I labeled the variables by what the treatment effect was supposed to be. Here I get the actual treatment effects I got from the tree, which is good. My code is correct. But also the standard errors are reasonably small, and so you can reject that these different leaves are the same as each other. But when I take this to the test sample, it turns out that almost none of that holds up. That the differences between the leaves are generally not statistically significant. Only one of the interactions is statistically significantly different than 0. And so what this is an example. We had 50,000 observations, 25,000 in the test sample, 25,000 in the training sample. I've only got 7 leaves here. There's more than 1,000 observations per leaf. Your intuition would say this, some spurious 3 observations couldn't have done this. But it turns out these machine learning methods are so smart that they're going to find collections of 1,000. If you give them enough covariates, they'll find 1,000 or 2,000 guys that are spuriously high and identify that leaf. And so my message out of this was that, you know, the focus on honesty in your estimation and inference is more important than my intuition would have suggested, and I think the machine learning literature has cared about. Now, they haven't really been focused on the inference at all, so that's not surprising. They haven't noticed it so much. And I think the same thing would come up in Lasso, and Viktor Chernozikov has some really nice work recently also kind of making that point, that really we need to, even when we're using regularization and cross-validation, we still maybe need to split our samples for model selection, search, and for estimation. So I hope you've enjoyed the talk. The big picture goal is that we're trying to do estimation of causal effects. We want to use our degrees of freedom in pursuit of that goal, even though there's no ground truth. There are going to be, I think, many improvements on what we're suggesting, so we're thinking of it as a sort of a first step in that direction. We hope we'll improve on it, and others will too. But those are sort of the themes. Heterogeneous effects, splitting out the causal part of the model. I'm estimating something at the leaf of the tree rather than y, and I'm doing cross-validation based on my objective. Thanks.